Madam, good afternoon.
Good afternoon.
It's a great pleasure to have you in the midst of all our children. We are so blessed to have you today. Now, on behalf of our Samiti, I request our Honorable Assistant Commissioner Sri Raghavan Kavalan to formally welcome you to the program, Madam. Please, over to you, sir. Yes.
Good morning, Catherine, Professor Catherine. We are very delighted to have you in our platform. I welcome you.
Thank you.
To address our children. Madam, this is a series of lectures arranged for the girl children in our country. Last year, our Prime Minister launched a new program called Vigyan Jyoti, especially for the girl children. Nowadays, what is happening is most of the children are running away for the lucrative job like IT and other job. A very few children are only selecting basic science for science and technology or in the STEM area, science, technology, engineering, and mathematics. So the scheme was launched mainly to attract and motivate the children towards basic science, which is very, very essential for our lively, for the entire world survive. So in that connection, in Navodaya Vidyalaya, you know very well about the Navodaya system because you are regularly a visitor in our Navodaya Vidyalaya, Bangalore, rural Dodaballapur. This is aimed at attract the children. So for that, we are trying to introduce people like you who excelled in their life as a role model in front of them. A series of lectures we are arranging. So we are very proud that you agreed to address our children. They are very happy. And for our viewers, just to give a brief profile about you, Madam. So dear children, Katherine Blundell is a professor of astrophysics at the University of Oxford and a supernumerary research fellow at St. John College, Oxford. Madam is a recipient of the highest order of Office of Order of British Empire. We call it as OBE. It is awarded only to the distinguished personalities for their excellent service in the field of science and technology and various other fields. She is a recipient of Rosalind Franklin Award, Royal Society, University Research Fellowship. She received a fellowship from Royal Commission for the exhibition of 1851. And she also is a recipient of Philip Leverenn Prize in Astronomy and Astrophysics. She also authored books, many books, in that the main one is Concept in Thermal Physics. The book covers kinetic theory, thermodynamics, statistical mechanics, and applications in astrophysics. And she's also a visiting professor of Astronomical Society, appointed as Gresham Professor of Astronomy. Professor Catherine's main area of research include astrophysics, study of black holes, and microquasars. She is concentrating mainly on research in the area of physics of active galaxies, such as quasars, formation of these objects and their life cycles, in addition to the interest on galaxies. She is engaged in studying the detailed spectroscopic measurement of the microquasars and related galactic objects. This is a new venture in time domain astrophysics initiated by Professor Katherine. This is called Global JetWatch. We are very known to her very well with that project. 5 gigantic telescopes are installed in various parts of the planet, which are separated in longitude around the planet, so that any time at least one of them is in night time. And we are very fortunate to have you here in this platform to address our children. And I am also fortunate to personally met Professor Katherine when she visited in JNV Dodaballapur, and she explained me the working of that telescope personally. I was very fortunate to have gotten such an opportunity. And our Navodaya children, especially Bangalore rural, they are also very fortunate to have a regular interaction with the children. She visits normally 2 to 3 times in a year in each global jet watch centers. And she remotely control all the operations of these jet watch centers by sitting in her place, in addition to visit. Madam, we are very fortunate, and I welcome once again you to address our children, and you are their role model. Now, before I request you to take over the stage to address the children, use this platform. Our former Joint Commissioner, Sri Ramchandra Sir, who is very instrumental in introducing this project of DST in our Navodaya Vidyalaya system, a very motivated person. He was always behind us for upliftment of the children. On behalf of all the participants and on behalf of JNV Bangalore Urban and Navodaya Vidyalaya Hyderabad, I request Sri Ramchandra Sir to address the gathering for a few minutes before Katherine take over the platform. Sir, please.
Yeah, thank you, Mr. Raghavan. It's an honor to keep an introductory note during the talk from Professor Katherine. Furthermore, like Mr. Raghavan has said, I'm also one of those fortunate who met Professor Katherine. In fact, a small note to our teachers and children, Professor Katherine adores the Navodaya system like any of us in the system. You will be really surprised to know. She has visited Navodaya, she sat with the children, she lived with the children, she ate with the children, and she has interacted with Navodaya children. Mr. Chakravarti is also in this platform today. He would also be able to vouch for this. Her deeper interest in supporting the children and bringing them to do science has been of great motivation. You will be really surprised to know she is a teacher par excellence. Never forced any child to involve in her activities, but the children are so much attracted to her works in such a way that even when I was in Hyderabad, children used to call me, sir, when do we get the telescope? How do we involve in that? What will be our role? How do we involve in these activities? Professor Katherine will be really happy to know that the activities just in the background you have started in the Navodaya Vidyalaya has pushed at least 5 children to do science in the premier institutes in the country. And today, one of our alumni is just nearer to you. He's doing his PhD in Manchester. Yeah, so he will be, I would request some time to meet you. And the world is so small. I was just sharing with Miss Ranjita about your talk today. She was so excited and said that one of the great human beings she has met in Professor Katherine. So this is how people who meet Professor Katherine feel. You don't feel that she is the scientist of that order, but still keeps the things to ground, and here she is to motivate you once again. I would at least be blessed to feel that at least 10 or 20 children who are amongst many children who come today for the talk get motivated to pursue astronomy. Thank you very much, Professor. And you will also be happy to know that in the past 3-4 years, some of our children have reached UK. 2 are in Imperial, 2 are in Edinburgh, one is in University College of London. Like this, one in McGill and the other one is Toronto. They have moved because of the support from Dr. Ranjitha. And I would give some kind of a credit to your project in the Navodaya, because we could also launch this and then tell them that there are great professors you aspire for studying in the great institutes. That's how we feel it very proud to have you with us. Thank you very much. I will not take much of time. Over to Professor Katherine. And children, you will also be happy to know that it is not Katherine alone who is pushing this. Her whole family, her husband is also a great scientist, and he also takes very deeper interest in Navodaya projects. So here you have Professor Katherine. Thank you.
So thank you so much for your very kind introduction. And I thank all of you for your very kind words of welcome to me. So good afternoon to you from Oxford. Oxford is where I am currently, and I'm very sad that it's 8,000 kilometers away from you just now. While it is truly a pleasure that we can share this time together and talk about interesting things beyond our own planet, I'm of course sad that I can't visit for some time until the world has figured out how to confront the challenges of this global pandemic. But thanks to technology, we can connect together and we can learn about interesting things. And so I'm going to begin by sharing my screen and I hope showing my first slide. And I trust that that's appearing okay to you in India. I trust that that's working. Thank you so much. So beyond our planet, here we are on planet Earth. You're in India, I am 8,000 kilometers away. But as I say, thanks to technology, we can be in touch and we can connect and we can learn from our rocky planet many things about the amazing space that lies beyond our planet. So let me take you first of all to our nearest celestial neighbor, the moon. Now, when you look at the moon, as you can do from your schools, from your homes, from your towns, whenever there isn't any bright city light or town light, you can see the moon. And it's particularly good at present because we are in full moon. When you look at the moon, you see that it is covered in craters, circular regions that have arisen because of rocky detritus that has smacked into the surface of the moon, having been pulled in from further out in the solar system and attracted by the strong gravitational pull of our nearest star, the sun. And as we zoom in and look yet more closely at the surface of the moon, and these images were all taken with the telescope in Doddaballapur that Mr. Ramachandran referred to a few moments ago, we see yet more deeply these craters. As I said, they're formed when things smack into the surface of the moon, particularly when meteorites, debris from the outermost parts of the solar system collide with the moon en route to the sun, to which they are attracted because of the strong pull of gravity. Now, I wonder if there aren't a few people who are listening today who are thinking, well, I think I understand now a bit about why there are craters on the surface of the moon, but how come we don't see many craters here on planet Earth? Planet Earth orbits around the sun, just as the moon orbits around planet Earth as it orbits around the planet, as it orbits around the sun. How come we don't see loads of craters on the Earth? Let's have a look at why that might be. Well, an important difference about planet Earth and our nearest celestial neighbor, the moon, is that our planet has an atmosphere. And if we did not have an atmosphere here on planet Earth, we could not breathe. It is that simple. We need an atmosphere to support life. We need oxygen. Plants need oxygen. The animals need oxygen. So it's important to realize that we have an atmosphere here on planet Earth because the gravity of planet Earth itself is sufficiently strong to hold the atmosphere onto our planet so we can breathe, so life can survive. That's not the case on the moon. The atmosphere means that when meteorites fly in from outer space, typically, because of the atmosphere, there is a lot of frictional heating. When things get hot, they burn up, and they can often be very bright, they can be like fireworks, they can be very beautiful. So let me in fact just show you an example of a meteor that came from a camera that we installed in January when we were last able to visit Karnataka. This camera is on the roof of the school, and I'll talk a bit more about that later. So the image that I'm showing you now is an image of the night sky. Let me explain what we're seeing first. So around the edge, you can see, I hope, a palm tree at about 1 o'clock, and you can see other trees surrounding the horizon. This camera has what we call a fisheye lens, and it is able to see 2 pi of sky from horizon to horizon. So what happened next? Keep watching the image of this camera. I hope you can make out a few stars on this image, but just keep watching and see if you see a streak appear. That streak, my friends, is the bright light of a meteor hurtling through the atmosphere and getting very, very hot. The exposure time of this camera is only 42 seconds, and yet in that time, you see the meteor streak through the sky. This meteor is a bit of rock about the size of a small apricot or a small grape. It's that tiny, but in being very tiny, because of the strong frictional heating through our atmosphere, it is very bright and it makes a big difference to our night sky. Let me just zoom in so that you can perhaps see this a little bit more clearly. So you can see the streak of the meteor. It's changing in brightness as it travels through the atmosphere. Maybe some of you who've looked at the sky can see in the top right corner that there's a set of stars in a particular pattern. That particular pattern we know as a constellation of stars, and we give it the name Orion. So you can see that that streak of a meteor formed from a little bit of rock, not much bigger than the size of a grape, can streak through the sky and light it up on a size scale that's comparable with the size of Orion. Zooming in even closer, we can see yet more clearly how that streaks through the sky. Now, the point is, that's what happens to a meteor or a bit of rock as it streaks through the Earth's atmosphere. But the point is, the moon has very low gravity. Because it has low gravity, it can't hold onto an atmosphere. It can't hold onto enough oxygen for life to be sustained. So because rock doesn't get burned up into meteors when it approaches the moon, it just goes splat on the moon's surface, forming those amazing circular craters. So I hope you realize we've just covered 2 reasons why it would be dangerous to think that you could safely live on the moon. First of all, there's no air to breathe. Second, you risk being hit by a meteor, but our atmosphere enables us to breathe, and it protects us from a lot of space debris and rocky debris that is attracted towards our nearest star, our massive neighbour, the sun. So I want us to think now about what else besides meteors gets attracted towards the sun. Ideally, we want to study something that moves a bit more slowly through the night sky than meteors, so we can actually study them. Something that only lasts for 42 seconds doesn't give us much chance to study it in detail. And so what I'm going to show you now is an image of a comet. Now, a comet moves at a rather more sedate pace around the sun, and so because it moves more slowly, we can study them more carefully. So I'm showing you here a comet which was discovered in 1999. The comet is the bright, hazy object towards the bottom right, just bottom right, lower right of center of the image that I've shown you. This comet was spotted a long way out, well before it got near the sun, so it could be studied a very long time before and after going round the sun. This comet was discovered by my colleague, Stephen Lee, whom Mr. Chakravarti knows well. He is the instrument scientist on the Global Jet Watch project, and he is a most amazing observer of the night sky. He knows it very deeply, and because of his knowledge of the sky, when something changes, when something is different from normal, he is alert to that change, he can recognize that change, and he can understand that change. And so what we see here is a comet that moves. The actual head of the comet, you can see it moving with respect to the stationary star background, gradually progressing through the night sky in a way that's different from how, let me just try that one more time so you can see it again. You can see how the comet is moving with respect to the distant background stars. Now, what's responsible for all that bright fuzzy light that comes from the head of the comet? It actually comes from different cyanide molecules. Cyanide is very poisonous to humans, but nonetheless it's something that forms in outer space. The size of the actual head of the comet is about the size of the school campus in Doddaballapur, or maybe a little bit larger. Towards the end of the 20th century, this comet headed past Saturn, and it won't actually return back to planet Earth or past planet Earth for another 146,000 years. So I'm going to show you now what we think its path is. Right at the very center of this image is our sun. And then you can see the orbital paths of Saturn and of Uranus and of Neptune. But the big line, white line coming in from the bottom of the screen, that is this comet. It's moving very differently to all the other planets and all the other stars. So that discovery was in 1999. I now want to tell you about another comet that was seen rather more recently. Specifically, it was seen this year, and it was seen since lockdown began. So this is an image of a new comet known as Comet Swan. Again, the image that I'm showing you was taken by my colleague Steve Lee in Australia. The field of view of this image that I'm showing you is about 3 degrees on the sky. And you can see its beautiful tail streaking behind the head. The tail of the comet is pointing away from the sun because the sun is actually blowing off a lot of gas and a lot of plasma. But this tail is unusually strong and unusually long for a comet. As I say, it's 3 degrees in extent. And if those units aren't very familiar to you when looking at the night sky, let me tell you that 3 degrees is 6 times the angular diameter of the moon that perhaps you might look out for tonight if it isn't too cloudy with the monsoon weather. So this comet was observed in May, just a couple of months ago, and you can see, especially if I zoom in, the beautiful structures within the tail of the comet. Now, most comets come from further out in the solar system, from the Kuiper belt, which is even beyond Neptune, or from the Oort cloud, which is even beyond Pluto, which is a very famous dwarf planet. Now, because of all the gravitational attraction in the solar system, which is dominated by the sun itself, which is a very massive object relative to the planets, the sun's gravity causes bits of rock, bits of debris to hurtle towards it. Now, gravity is an amazing thing because if you've got enough mass, as you have with our nearest star, the sun, it causes things to hurtle towards it. But I don't want you to think of gravity as purely a negative thing. Gravity is also what is responsible for holding the planets in orbit around the sun in our solar system. Now, if we didn't orbit around the sun, if planet Earth didn't orbit around the sun within its path in the solar system, we wouldn't have birthdays. Now, did you know that since the founding of the very first JNV school in 1986, planet Earth has orbited around the sun some 34 times? Isn't that amazing? Hooray for gravity. Well, let's think a little more about what is our place in space. It's the combination of the law of gravity and a few other laws of physics that sustain the orbiting of planets around the sun. One of those important laws of physics is something that we call the law of conservation of angular momentum. Angular momentum is the property that a body has because it's orbiting or because it's spinning. Angular momentum is something that physicists love to talk about, and I'm sure that your physics teachers would be delighted to talk to you about it and show you some demonstrations. That gravity and the conservation of angular momentum are crucial not just for sustaining planetary orbits, but also for their formation. And I'm going to show you a little bit about that in just a moment. So what does our solar system consist of? It consists of a normal star, the sun. It consists of 8 planets. It consists of loads of dwarf planets, besides many comets and asteroids and all the rest of it. But consider this. What circles the sun in orbit around it in the solar system has a mass which is less than 1,000th of the mass of the sun itself. Isn't that amazing? We are so insignificant in terms of mass, and yet we orbit the sun sustainably, repeatably, year in, year out. So what else does gravity do for us besides sustaining that orbit? Well, gravity promotes collapse. Now that may sound like a very negative thing, but without the collapse of matter, we would not have the formation of planets. We would not be here. The graph that I'm showing you here is designed to just show you in a schematic way, if you've got a couple of lumps of mass, then those overdensities of mass, those bits of extra mass, will gravitationally attract themselves and collapse and collapse and collapse. If you've got excess mass, that will always tend to collapse. So that's what gravity does for you. What does angular momentum do for you? Well, it affects shape. Now, this can be hard to take on board, but I'm going to show you how we can visualize how angular momentum changes shape. What I want to emphasize to you in the movie that I'm about to show you is that it is the combination of angular momentum together with gravity. It's the two working in concert that give us some of the spectacular things that we can see in the night sky. So watch this movie now. What we're looking at is a movie of a cloud of gas that's gradually rotating because of its angular momentum, but under gravity, it's also gradually going to collapse. So as these gradually work, you can see the matter is collapsing into a plane, but angular momentum keeps it spinning. The combination of gravitational collapse into a plane while the angular momentum keeps us spinning gives rise to the formation of planets that orbit around the central mass. Gradually, the central mass gets brighter. It's got enough mass that it gets sufficiently hot that nuclear fusion can take place and we have a star. So I hope you can see on the outermost edges of this collapsed gas cloud, we've got some little planets with their own disks. So I'd like to emphasize, so now you can see even more clearly that it's a star at the center, much like our sun, with planets in orbit around it. Let me take you now to what happens when we get a planet with one of those little disks around it. This thinking is prompted by the computer movie that I've just shown you. Let me be very clear, this is a simulation of astrophysical evolution that we believe to have taken place and given rise to our solar system and other planets around other stars elsewhere in our galaxy. There's no way that even the best observations with the most advanced telescopes could give us that image. And that's because the timescales are so much slower and longer than human timescales. Please God, we might live for the best part of 100 years, maybe. But the kind of processes that I've just shown you in this movie, they take place over millions of years. And so those are not human-friendly timescales for us to make observations of. But computer programming, computer simulations, computer calculations play an important role in transcending the limits of our ability to observe here from planet Earth. We can go beyond planet Earth with clever calculations on our computers. And I'd really like to encourage all of you, if you have a bit of time in the coming months, for whatever reason, try and think if you could learn how to code. Try and think if you could learn the basics of how to write computer-controlled instructions. It's extremely interesting, it's extremely rewarding. But as I hope this movie showed you, it's extremely powerful as well. And the ability to write computer code will help you in all walks of life. It's great fun. I really recommend it. Okay, back to outer space. Now let me take you to planet Jupiter. So this is an image of Jupiter and some of its moons that was observed at the telescope in Doddaballapur. I started this talk talking about our moon. Our planet Earth has one satellite orbiting around it, but other planets in our solar system have very many more moons. This has been known for many centuries. It was actually about 4 centuries ago that the Italian observer, Galileo, discovered the 4 bright moons that you can see on this image here. And so we name them in his honor. They're called the Galilean moons. But we now know that there are over 70 moons, 70 satellites in orbit around Jupiter, formed because of the combination of gravity and angular momentum that I hope my previous movie indicated to you. So let me just show you an image of the telescope in Doddaballapur that took those images, and some of the students at the school who in the past few years have observed Jupiter. Jupiter is a favourite topic, and I love it a favourite target, and I love it every time that someone chooses to observe it. So let me just take you through the 4 moons of Jupiter. The one that the arrow is pointing to now is known as Ganymede. It is the outermost moon of the 4 Galilean moons. Do you know it is larger than the planet Mercury? And this is just a moon around planet Jupiter. And it orbits Jupiter every 7 days. In 1 week, Ganymede, the Galilean moon, which is larger than the planet Mercury, orbits around Jupiter. It's astonishing. Next up is Callisto. Callisto moves at a more leisurely pace. It takes 17 days to orbit around Jupiter. It's about the same mass as planet Mercury, but it is much less dense. It's only about 1/3 of the mass of Ganymede. Now let's go to the next one. This is Europa. Now Europa is the smallest of the Galilean moons, and it orbits Jupiter every 3.5 days. So that's nipping around there pretty quickly. And then finally, the nearest planet in this image is, the nearest moon to the planet Jupiter in this image is called Io. Now Io orbits Jupiter every 42 hours. And something I love to do with the students at the telescope is to observe Jupiter, and then a bit later, say 20 minutes later, take another image, a bit like the one that you're looking at on the screen, and you can see how some of the moons have moved. One day it's my ambition to do 42 days of sampling the movements of the Galilean moons, not just with the telescope in Karnataka, but with all the other schools around the world. But I'll come back to those other schools later on. So Io is always the moon that moves most rapidly in any image of Jupiter that you might observe. But there's more to Io that's remarkable than just how fast it moves. Io is volcanically very active. On the moon of Io, there are over 400 active volcanoes. If you consider the number of volcanoes per square kilometre on planet Earth, and there aren't a lot in India and there aren't a lot in the UK, thankfully for us, but if you average that number over the whole planet, Io has 10 times the number of volcanoes per square kilometre than we do on planet Earth. Volcanoes are going off constantly on Io. So it's a very interesting moon to study further out in our solar system. So that's where Jupiter sits in the solar system. I shouldn't say sits, of course, because it's constantly orbiting around. But I now want to turn our attention to the sun itself. Now, I hope we all know, I'm sure we all know, that you must never, ever look at the sun directly. It would be desperately dangerous for your eyesight if you did. So you never, ever look at the sun. But just occasionally, the behaviour of the solar system means that it's possible to look in the direction of the sun because we've blocked out the bright bit of the sun. This is what happens when we get a total solar eclipse. It's when the moon, our nearest celestial neighbour, moves exactly in front of the sun. And this happens not infrequently, every year and a half or so. And with special filters, which I was using to take these images that you're now looking at, what you see, the white crescent is actually the sun, and the black circular disk that's starting to block that out, that's actually the moon. Now, the moon doesn't radiate any light, it only reflects sunlight. So when we're looking at it against the sun in this way, with the help of a special filter, I'm not looking at the sun directly, nor is my camera when I'm taking these images. You can see that the moon fits rather amazingly over the sun. Now, when they are exactly lined up and we've blocked out the dangerous part of the light, then and only then is it safe to look at the sun. And the image that I'm showing you here is an image that I took 3 years ago in North America, and it shows the corona of the sun streaking out and illuminated by magnetic field lines that perhaps you can see some impression of in this image. Perhaps you can also see some pink features on this image. Let me zoom into those. These prominences from the sun are where the sun is explosively sending out highly energetic, very, very hot plasma out into the solar system. And we can actually detect the consequences of that here on planet Earth. But I really want to emphasize to you that the sun, although it's very steady in terms of its mass and keeping our planet in orbit and all the other planets in orbit, though it's very steady in mass, energetically, it's very active. And we can get glimpses of this on those rare occasions when an eclipse means that it is safe to look at the sun. It is never safe at any other time. So I've indicated to you that the sun is energetically very active, but in fact, all across space, there is activity that is teeming away if we have the technology to look at it, if we're in a position to observe it appropriately. So while this is the sort of image that we can see on a dark night, if there aren't too many house lights or city lights that are contaminating our vision of the night sky, this is the best kind of image that you could hope to get with human eyes. What we're looking at here are lots of stars. Right at the bottom, you've got the moon and you've got the planet Venus at the bottom of the image. Everything else you see there is stars. And this is comparable to the kind of image you could hope to see when it's very dark on planet Earth. Now, again, do you remember Orion that I mentioned earlier in that all-sky camera image? A constellation of stars that we can see in the winter months. Trained eyes, I wonder if you can see it on this image as well. Let me outline for you the different stars that appear in Orion. And I hope that you're able to make out some of the different stars that appear in Orion. This image was taken from Australia, which is why it may look a little unfamiliar to you. So with trained eyes, even without telescope assistance, our trained eyes can see things that we can become familiar with, that we can recognize in the night sky. But I now want us to think about what we can see in the night sky when we start to use cameras. When we use a camera, we can collect light for a longer time than we can collect with our eyes. Our eyes typically collect each imageful, each eyeful, for about 1/5 of a second. The camera image that I'm showing you now was an exposure time of about 1/2 minute, 30 seconds. So that's a lot more light that can be collected than in 1/5 of a second. So that means we can see more deeply into space. We can see more stars and more interesting things. And as we study the sky more, we see that it is not static and unchanging, but that it is dynamic and evolving and explosive. And this is pretty exciting and good fun to study. And so this connects up with my area of research, which is variable stars in our galaxy, variable stars of different sorts, black hole stars, white dwarf stars, nova stars. And I'll explain a little bit about those to you later on. But first, let me tell you something about how I go on and do my research. So, as Mr. Ramachandran indicated, I have set up with my colleague, Steve Lee, 5 telescopes around the observatory. They are separated in longitude so that there is always at least one in darkness. And if you think of the perspective of a star, say, in the top left of the image, you'll see that gradually the stars, the planet, the telescopes on the planet take it in turn to be able to look at one of those stars. And so that means we can monitor it very closely round the clock. Of course, that's not possible during monsoon season, but we're very thankful for monsoon because it brings us the rain that we need for our crops and for our food, important for sustaining life in different ways. So with this network of 5 telescopes, it's possible to study the night sky in the way that we want to for our astrophysics research based here at the University of Oxford. I'm going to show you just a few pictures now of some of the telescopes. This is the telescope in South America, in Chile, at the school there, looking up at the night sky. This is the other end of, they're identical telescopes. This is the back end of the telescope here in India. And this is a montage of all the different telescopes. There are 2 in Australia, 1 at each end, and there's also 1 in South Africa. And I really cherish the relationships that we have with the schools that host each of these telescopes. That's very special indeed. Let me show you a little bit about the schools. There's one that will be recognised by many who are watching today. Let me take you to this one in South Africa. So the whole idea is that the girls at this school, as at the other schools, are free before local bedtime to observe targets that they want. Now, of course, this only works when it's not raining. And you can see some of the girls here designing and planning their observations. And I'm delighted that the students in Dodabalapur make such good use of the telescope. I have to say, it's a real joy for me to visit the J&B school in Dodabalapur. The students that I've met there have a thirst for knowledge that I've not seen anywhere else around the world. They love to ask good questions, and that's a very, very precious thing indeed. I love the fact that they ask such good questions. I love the fact they have such a thirst for knowledge and that they make such good use of the opportunities afforded to them by Mr. Chakravarti and his dedicated team of teachers. It's a real treat for me to visit, and I so look forward to when lockdown is over for so many reasons, but one of the important ones of which is that I can visit India once again. Now, I'd like to just mention to you a practical reality of living on planet Earth, and that is sometimes the lights go out. Sometimes we lose electricity. And this happened to us with our observatory on the school roof in Dodabalapur. So I want to tell you how we confronted that challenge and how we overcame it. The answer was to obtain power from our nearest star. Mr. Chakravarti kindly gave me permission to install a solar farm on top of the school roof. So let me just show you a few pictures of that. This is the steel that was delivered to build this shed to keep the batteries in, to store as chemical energy the light energy that comes from the sun. This is inside the shed. These are the various devices that regulate how the solar panels on the roof collect the light energy, convert it to electrical energy, and then ultimately via big thick cables that we checked very, very carefully. This is my colleague Steve Lee and our colleague Chris McCowage. We checked everything carefully and it's worked beautifully, reliably. The electricity is sustained thanks to energy from our nearest star. These big batteries here show you how we store as chemical energy light from our nearest star. This is now on top of the roof, looking back towards the observatory as we mounted these very strong steel supports that were designed to be strong enough to hold onto the solar panels so that even during a storm or a wild wind, and we do know life does bring its storms and its trials and tribulations, we made absolutely sure that this was strong enough to withstand all of those. And it works beautifully reliably. And here you can see the size for scale. So with that infrastructure designed and made to be resilient and robust, we're in a position to study many exciting astrophysical phenomena beyond our planet. So what do we study? Well, let me take you back to this image of the night sky, which shows across it our Milky Way galaxy. That's the big streak. If I zoom in, I hope you can see on the right-hand side, there are some red rings. I'm going to zoom into those red rings with an image taken by the telescope. Actually, this particular image was taken by the school observatory in Chile. If we zoom in and zoom in a bit more, we're now looking at the region of sky where we had those red rings originally when we could see the whole of the Milky Way. Now, if I zoom in to, if I just show you those two stars, those two images, I wonder if you can see that in the one without the red rings, there's a star missing, but with the red ring, with the red rings, there's a star there. That star newly appeared just a couple of years ago. And so because I like things that change, because I like things that are energetic and explosive, we started observing it. So this is what's going on at the very center of those red rings that I indicated to you. So here we go. So right at the very center of those red rings, there are two stars that are orbiting one another. There's a normal star, much like our sun, and that's the one that's colored red in this image that you're looking at. There's also a type of star which is very, very compact. It's collapsed a lot under gravity, and it's called a white dwarf. Remember, we talked a lot about gravity earlier. So gravity attracts hydrogen gas from that red star, and it attracts it sufficiently energetically and sufficiently rapidly that when the hydrogen from the red star lands on the surface of the white dwarf, it thwacks onto that hard surface and the temperature goes up and the pressure goes up. Now, when you have got high pressure and high temperature, you have then got the physical conditions necessary for nuclear fusion. Nuclear fusion is very important for chemistry. If nuclear fusion as a process did not take place in this universe, there would be no life. Okay, so we're very happy that you get these explosions in space because ultimately they give rise to the interstellar gas, and it's the interstellar gas and dust that occasionally can gradually collapse down, rotate under gravity, and form new solar systems, much like the image that I showed you early on in my talk. When this process happens of hydrogen being attracted from a normal star, collapsing, smacking onto the surface of a white dwarf, and you have high pressure and high temperature, you get a thermonuclear runaway reaction. This releases enormous amounts of energy. I feel sure that those of you studying physics will have an idea of what 1 joule of energy is. Well, a nova explosion releases 1 times 10 to the power of 37 joules of energy. That's a 1 and 37 zeros after it. It's such a large number, I don't know how to pronounce it any other way. It's a huge amount of energy. I try and think about the most energetic things you've ever heard of. Think of a nuclear explosion, which sadly has taken place here on Earth. In 1945, just before sunrise, in the desert sands of the Trinity site in New Mexico, an atomic bomb was detonated for testing. It was developed as part of a major effort called the Manhattan Project. And I really wish that similar effort and focus could be given to address the averting of climate change, which is afflicting this particular planet now. We're in the midst of it. When collective scientists come together and focus, and they have the resources they need to investigate different things, they gain new understanding and can figure out clever and remarkable things. We need to do that for climate change, but right now, historically, this is a focus that happened relating to nuclear bombs, which is not a happy topic, far from it. But it illustrates that when you understand the underlying physics, you can do remarkable, if very shocking things. Now, the energy given off by this explosion in that desert in New Mexico was so large and the temperatures were so hot that sand in the desert melted. It fused into pieces of what looked like glass. It's called trinitite. I visited that desert with very heavy heart, with much sorrow in my heart a few years ago. And I saw these pieces of glass. They look like big bits of molten glass, slightly green color. They're called trinitite, after Trinity site where this took place. But the energy from this was only 100 terajoules. A nova explosion in the night sky is 10 to the power of 23 times more powerful than the most powerful bomb that humans could create on Earth. So we're dealing with enormous explosions in outer space. Of course, the biggest explosion of all was what we call in cosmology the Big Bang. 1 second after this, we got a very big explosion, and that's when conditions were very, very hot and all sorts of nuclear physics processes could take place. Subsequent to that, the universe expanded and cooled, and that meant that electrons and protons were able to get together and form hydrogens. But if only hydrogen could form in the universe, we wouldn't be here. The computer technology by which we can talk to one another is based on silicon. You and me, we're based on carbon and oxygen and nitrogen and things like that. There is more to life than hydrogen. And in fact, when you get a nova explosion, on the surface of that white dwarf star, benefiting from the hydrogen gas that's ripped from that normal red-coloured star that I showed you earlier, you get a thermonuclear runaway and all kinds of nuclear physics chain reactions. And that's when all sorts of different chemical elements are created. This happened to an extent in the Big Bang, shortly after time began for our universe. It also happened for, and continually happens to this day, in outer space whenever nova explosions or supernova explosions are taking place. And we get all sorts of different heavier chemical elements formed. So what are those? What kind of elements do we need? Well, I'm listing here a list of different elements that humans need in order to be able to live and move and have our being. So all of these different foods we ingest from eating all sorts of different vegetables and rice and all of those kind of good things. These all have their place in the periodic table. And we owe the chemical elements to a combination of explosive events that happened in outer space. First of all, to the Big Bang, but then to ongoing nova explosions and to the more rare but more energetic events to supernova explosions. Well, that's nova and supernova explosions. I just want to talk now a little bit about black holes. As Sir mentioned at the start of my talk, black holes are something I love to study. So let's go back to that image of the night sky with the Milky Way, the galaxy, streaking across it. You can see some red rings now in a different place. They're just to the left of the center. This is the exact same image of the night sky. It's just the red rings that have moved. And what I'm going to be talking about in the next few minutes is a star at the very center of those red rings. Now, anyone who's visited the observatory on top of the school roof in Doddaballapur knows that there's a shiny red box in there at the foot of the telescope. That shiny red box contains a very important, very precious piece of equipment. It's called a spectrograph. And what it does is to split up light from a star into an entire spectrum of different colors. Physicists know this as different wavelengths. So a spectrograph splits up starlight into a spectrum in much the same way that raindrops in a cloud split up sunlight into a rainbow. It's the exact same physics that we're using. But let me show you what happens when we use the global JetWatch telescopes to look at the star, which is actually a black hole, or a black hole orbiting around a normal star at the center of the red rings that you're looking at right now. What you see is a spectrum of light from that star. You see it stretched out into blue light on the left and more red light on the right. What we're really looking at is how the intensity of light from that star changes with color or with wavelength. Now see what happens when I look 24 hours later. It gradually changes, it suddenly changes, and you can see the lines move apart. If you look long enough, they move back together again, then they go apart again. So it's pretty remarkable that we can see these changes in this black hole system from the school roof in Karnataka. What I'm showing you now is just a little montage of about a week's worth of data from the India telescope. Now I want you to imagine what happens when I'm collecting data round the clock from all of the global JetWatch observatories, and I collect them and I analyze them. So there are certain calculations that we've developed on these spectra, looking at the positions of how those bright emission line peaks move backwards and forwards. And by doing a geometrical calculation, we can make predictions of how we think the star will look in the future. So these are spectra taken absolutely of the central black hole orbiting around the star, right in the very center, we can make predictions at how sometime later, say a year later, we think the matter that is indicated here by these emission lines, but corresponds to matter being squirted away at great speeds from near the black hole, we can make predictions of what it looks like, say, a year later. And so I did that. And you can see just a selection of spectra from all the different schools. I'm not showing you here the calculation that we did, but in that central panel, I'm showing you red and blue dots, which show you what my prediction is for what the pattern of material squirted out from nearby that star should look like a year after I've taken those data from the global Jet Watch telescopes. So how do I test my prediction? A big part of science is testability and falsifiability. You need to make a proposal, a prediction, and you need to robustly test and analyze whether you're right. And the thing to realize in science is that making a prediction which doesn't turn out to be correct isn't failure. It's actually progress, because we've learnt something. The universe isn't as we thought it was, therefore we have to go back to the drawing board and rethink and reconfigure and reanalyze and come up with a new theory or a new conjecture. So let me tell you how I tested whether or not this pattern of red and blue dots would be correct. I needed to use a different kind of telescope, specifically a radio telescope. So what we're looking at now is an image of a radio telescope up in the desert in northern Chile. The data that we needed to test our theory was taken from this telescope 2 weeks after a major earthquake hit Chile. We live on a dangerous planet, but thanks to wise and clever design, buildings and telescopes survived that major earthquake. And thanks to mobile technology, people were warned to get away from tsunamis, resulting in very little loss of life, given what a strong earthquake it was. So we used this telescope that you see here. It thankfully survived the earthquake. This is just a zoom in. This is my prediction. And I'm going to overlay on this the outline in grayscale of what we actually observed from that grey telescope. And as you can see, we got agreement. We were very, very happy that we could make the prediction, and so we published it in one of these journals. And this massively confirms our thinking on black hole behavior, how black holes rip material from nearby stars under gravity, and how it swirls towards the black hole and then is spat out in a way that waves and wiggles and processes in the way that you see on this image. I want to close with just a couple of thoughts. So the reason that we can be in contact today when the world is in lockdown is because of technology. It's because of the internet and from computers. Did you know that Wi-Fi, the 802.11 protocol, rose out of a study of black holes? Some clever radio astronomers in Australia really wanted to search for the signature of merging black holes. And in pursuit of the instrumentation that was needed for that astrophysical endeavour, they developed an interference suppression algorithm that meant that led in a very direct way to the 802.11 Wi-Fi protocol. In pursuit of pure science, if we pursue science creatively, intelligently, conscientiously, with a wide global perspective, we can make a big difference. And so I want to close with a question for all of you. In whichever part of India you're sitting in now, and in whatever your circumstances, I want you to think not right now about the present and the past. I want you to think about the future. Specifically, I want you to ask yourselves, do you have what it takes to become a scientist? If you respect maths, better still, if you love maths, you have got the makings of a scientist. If you don't yet love maths, I really encourage you to practice. Like any other skill in life, mathematics comes with practice. And when you realize you can do something, you become good at it. When you become good at it, you start to enjoy it. If you are on that path of learning mathematics, walking towards loving mathematics, keep on that path. Work really hard at your mathematics. It will open doors for you in tomorrow's world. I wonder if you can ask good questions. I absolutely know that the students at the JNV school in Doddaballapur are very good at asking very good questions. So can you question the dogma? Can you think about what you're told and ask questions of yourself, of books, of your teachers, to satisfy yourself that you really understand what is being said to you? I really encourage you to develop the skill of asking good questions, because that is on the path to understanding. I wonder if you can hold more than one idea in your head at a time. That's what you have to do as an engineer, as a scientist. You have to be able to hold together lots of conflicting constraints, lots of different important principles. If you can hold more than one idea in your head at a time, you're on the path to becoming a scientist or an engineer, which this world so badly needs. I wonder if you have this skill. When you learn new information, when there is new evidence, are you big enough to change your mind? As scientists, we are always seeking and searching new information, new evidence, new measurements, new observations. These new data, this new information enables us to change our minds and refine our understanding of the way the universe is. It's crucially important for all of us to get really good at this skill of responding to new evidence at the same time as retaining the perspective of all the evidence that we've gathered up to this point. Going back to holding lots of ideas in our minds at the same time. Now, can you figure out imaginative solutions to problems? Can you approach problems and challenges creatively? That's really critical for any endeavour in science, in engineering, in technology. Absolutely critical. Also, you need to know that details matter. This is part of holding lots of ideas in your head at the same time. Details make the difference between having a reliable power supply, having a working telescope, and having none of those things. Details really matter. Now let me emphasize, none of these things that I've listed on this slide, none of these come instantly or immediately. None of us is born with these things. Note that I have not listed on this slide any dependence on your starting point in life. But I know that each one of you that has the immense privilege of attending a JNV school has got the most fantastic opportunity. JNV schools mean opportunity. And I really encourage you to seize the opportunities that you have been given from your dedicated teachers. In combination with that, I encourage you to make the most of your talents, to develop those talents, to grow those talents. And taking advantage of those two things and making the most of them and using your talents and opportunities to the full, I think that you will be able to give the most to this very needy planet. And so with that, I will conclude my talk for this afternoon. Thank you.
Madam, thank you very much, madam. Some questions from the participants. It's all right, madam?
Of course.
Yes. Satyalingam sir, anything is there? Okay, by the time they are getting ready, I go one doubt, madam. Okay, now you mentioned about that on the surface of the moon, there is no atmosphere. Due to that, it is very dangerous to stay over there. But as you know, some of our countries, they made the mission with the purpose to have human inhabitation, either on moon or this Mars. Though on both the celestial bodies, they have collected some data. Now, what is your opinion? Which is the better destination, better or feasible destination for us to have human inhabitation, whether it is moon or Mars? Please.
Well, I think that visiting both the moon and Mars are very exciting prospects. There are many benefits from visiting both, not the least of which is that we gain more data, more information, more evidence about the formation of the solar system. So it would be a wonderful thing to visit the moon and to visit Mars. If you go to the moon, there's no sense in which you could go there wearing the clothing that we are all wearing today. You'd be in a spacesuit with a big helmet. You'd be reliant on a tank of oxygen to enable you to breathe. So it wouldn't quite be life as we know it. On Mars, it would be even more dangerous. One of the other things I didn't mention about the danger of not having an atmosphere is that, or rather not having a magnetized atmosphere, is that all the plasma that is ejected and squirted out from the sun lands directly on the planet and will give you all sorts of radiation poisoning. So we should be under no illusions. We couldn't live on Mars or on the moon or anywhere else in our solar system and enjoy life as we know it. But we could go there for exploration, and I think it's very important for human beings to explore. So I can certainly see that there are many merits of doing this.
Okay. Any Nagabhaskar ji, any doubt?
Yes, sir. Yes, sir.
Please, carry on. Carry on.
Good morning, madam.
Good morning.
Madam, just a small query. As we know, the composition of the celestial bodies varies, right?
Yes.
This variation is due to the differential temperatures and pressure, or the gravity, or the different origin. Just I wanted to confirm it. Because it is formed from the cosmic dust itself, they say it. But truly speaking, the meteors and this thing and this variations occurs. So what is the real reason for these variations?
Thank you very much for that. In fact, the answer is that both are correct. So in the computer simulation that I showed early on in my talk, the gas cloud that collapsed wasn't homogeneous. It wasn't the same uniform composition throughout. And so that made a difference to the different planetary systems that formed at different distances from the central star. But there's something else as well that I didn't really touch on, which is that a lot of the bigger stars are very gaseous, very woofly. There's no sense in which they have a hard surface that you could walk around on. But planets that formed, the planets that are closer to the sun, they're much more rocky. They have hard surfaces typically. although there again, they have atmospheres you just wouldn't want to breathe. If ever you had the misfortune to land on Venus, it's very, very rich. Its atmosphere is very, very rich in carbon dioxide. And that planet has undergone a runaway greenhouse effect, which, if we're not careful, could happen here on planet Earth.
So that by analysis of this meteors and all, we can know the origin of this. Can we know from which planet it has been come, or from which area at least, not exactly the planet, nearby the system?
Yes, we can to some extent. So it's possible for meteors to come. So the majority of meteors come from the furthest points of our solar system, typically. Some from a bit closer in the Kuiper Belt. Very occasionally, it's suggested that some come from a different solar system, but they're very rare and hard to be very sure about. But certainly we can see some systematic differences that enable us to say, was it from the most extreme parts of the solar system, or was it from here? You're absolutely right. And analysing the composition, for example, seeing how much iron is present, how much nickel is present, that enables us to do the kind of analyses and calculations that you suggest.
Thanks a lot. Thank you.
Thank you.
Sir, Sadhilinga sir. Okay. Madam, if not there, one more small doubt, madam. You talked about these black holes, madam, black holes. Now, is the dimension of the black hole is ever what you call expanding, or is it constant?
The diameter of the black hole, by which I think you mean the diameter of what we call the event horizon of the black hole, that surface of no return if ever you pass through it, that won't change unless the mass of the black hole in the center changes. So that surface has a constant diameter if the mass of the black hole at the center is not changing. However, black holes are greedy and they are very strong gravitational attractors. So a lot of the time they are accreting mass, they're attracting mass. Black holes are very messy eaters, which is why we can see them a lot of the time. But gradually, as they accumulate more mass, as more mass penetrates that surface of no return, the event horizon, the mass of the central black hole gets bigger and the mass of the event horizon gets bigger. So yes, under certain circumstances, it can absolutely change and increase.
Changing. In the process, it gets increased only. Okay, okay. Okay, sir, any other doubt? Should we go for proposing vote of thanks, madam? Now, Chakravarti sir, on behalf of our Navodaya Vidyalaya Samiti, I request just our colleague, my friend, Mr. Chakravarti, Principal of JNV Bangalore Rural, to propose vote of thanks to our madam. Please, sir, over to you.
Hello.
Hello, sir.
Yes.
Good evening, sir. Is it audible? Come, sir.
Audible, you come unmute the video. Unmute audio video.
Sir, it is audible. Carry on.
Hello. Is it audible, sir?
Audible,
Yeah.
sir. Carry
Hello.
on. Yes,
Yeah.
audible. Please carry on.
Yeah. Sir. Good evening, sir. Good evening to everybody. It's a great privilege for me to propose vote of thanks, and it's a great occasion. And my thanks goes to Ministry of Science and Technology officers, our Honorable Commissioner, who is a mentor for this patron, and especially our A.N. Ramchandra sir, and who is instrumental in this program, and who has who spirited it. And to Madam Professor Katherine, Professor Astrophysics, Oxford University. Really, it's a amazing the topic that she has chosen, the beyond the planet. By standing comfortably beyond the planet, she has taken us to complete galaxy. To see the crystal clear galaxy from the madam's topic. In the Ramchan sir words, if you say, it will take some more time to digest the tablets given by Professor Katherine madam, no doubt. But still, our currents are raised many issues and many doubts which are very relevant to the topic. Madam has very clearly cleared. And I am very fortunate enough to see Comet, Stephen, personally, the scientist, Comet both. I am so lucky enough to see the both Comet and Comet Lee and the Stevens are complete. And physically, they come to our school, especially Madam, Katherine Madam and her team. They interact with the children and our physics sir and other colleagues. And it's very opportunity for the school, JNV Thottapur given, is we take the complete state government children also sometimes to interact with the madam under the pace setting activity. It's a great opportunity, and even the district officials appreciate many times to have such a wonderful instrument, having the 5 crores worth of it in our school. And it's a very elaborative, the extensive lecture and topic developed by madam. I'm extremely thankful to madam. I'm looking forward to see madam once again in JNV Thottapur as a Bangalore rural. Coming to our assistant commissioner, Sri Raghavan sir, especially our Kannan, my colleague, for everybody, I should be thankful to everybody for having made this program successful. Thank you, Runda. Thank you, Kannan sir. Thank you very much.
Thank you, sir. Thank you, sir. Thank you, sir. Madam, Madam, anything more to share? I think Mr. Sir Thiran also there from Shillong region. He is participating. Thiran sir, okay. Okay, sir. Then, Madam, should we wind it up? Hello, Madam.
Hello.
Should we wind the program or anything to share?
Only that I deeply thank the Commissioner, yourself, Mr. Kannan, Mr. Chakravarti, as always, all the principals and teachers who do so much for the JNV schools. Thank you, all of you.
It's our pleasure, madam. Thank you very much, madam. Thanks a lot. Thanks a lot.
Thank you. Goodbye.
Kindly visit our school. We'll meet in person. Thank you.
Definitely. Thank you.
Please. Okay, the program.